Good morning, everybody, and thanks for joining us on the Survey and Spatial webinar, How to Quality Assure Point Clouds. As usual with our webinars, if you have any questions at all throughout the presentation, please pop them in the Slido Q&A box, and our presenter will answer those for you at the end of the presentation. So once again, thanks for joining us today, and I'd now like to introduce our speaker for the day, Kirsty Mackie of Global Survey.
Hello.
Okay. There you go.
Sir, they're in.
Yes, we have it.
You should be able to see the chemical plant architecture.
Which one's Bond?
He's the Psy, he's the trident thingy.
Give us a layout.
Right.
Now, with our point clouds, we're not so much interested in locating James Bond as we are in the layout information that they refer to in that clip. But that layout information for us in the AEC industry generally has to be in the millimeters. So whilst you can go out and scan with a $1,000 iPhone, that point cloud is going to be significantly different to a $100,000 laser scanner. That's the crux of this presentation. How can we quality assure point clouds, and how can you tell a good point cloud from a bad point cloud? On the agenda for today, I'm going to start very broad and narrow in. That's important for this presentation because right now I'm speaking to 200 of you and you all have very different interactions with point clouds. Some of you will be receivers of point clouds, some of you will be modeling from them, and some of you will be producing them. So how am I going to tackle this, the wide variety of you? Firstly, I'll be looking at reality capture in general with a bit of a point clouds 101. Secondly, I'll be doing an overview of general checks you can do across different point clouds. And then thirdly, I'm going to go over some field techniques. This will be mostly focused on terrestrial laser scanning because that's where my main experience lies. But this should still be useful for non-point cloud producers and different types of point cloud interactions. So whether you're doing UAV photogrammetry or airborne LiDAR, this should also be helpful to you. But first, a bit more about me. I've dived right into this. Why am I here and what do I know about point clouds? I'm Kirsty Mackie. My background is in geography, where I focused on ground-based photogrammetry for analysing the shape of landforms for erosional changes and then monitoring this change over time using GIS. You can see one of the point clouds, the first point cloud I produced actually, at the top of the screen, there's a photogrammetric point cloud of Fox Glacier. And then on the right is some GIS outputs that I had for analysing the volumetric changes from DEMs I created from that. Since uni, I've worked in survey technician roles, firstly at Asbolt, focusing on scan to BIM and 360 imagery outputs. Whilst I was there, I was capturing hundreds of scans a day. So for those of you that are experienced in scanning, you know when there's more scans involved, that's where all the problems can happen. Anything that can go wrong will go wrong. I then worked at an engineering firm called Becker, focused in the survey section on terrestrial laser scanning. And I now work at Global Survey as a business development manager for Leica laser scanning technology. I've taken a lot of care to make this presentation hardware and software agnostic, so I'm focusing on the higher level principles of quality assurance through this. So a disclaimer, I'm not a trained surveyor. I haven't properly used a total station, but I can help you identify errors from your total station in your point clouds. So let's start really broad then. What is reality capture? Reality capture in the broadest sense is capturing the real world and creating a 3D digital representation of it. I love that definition because it's so simplistic. This is exactly what surveyors have been doing since day one. Capturing the real world is what survey is always about. It's what it has always been about and is all about. But the term reality capture is newer, and when people say it, they're typically referring to technology that can create point clouds, such as UAV, airborne LiDAR, terrestrial laser scanning. These tools have all stemmed from the principles of traditional survey. And when I say traditional survey, I mean traditional by modern day standards, so total stations and GPS devices. But As GeoWeek has said with this diagram on the right, traditional survey is the foundation and key element in collecting accurate data that is in project coordinates. So using these newer reality capture methods in conjunction with traditional survey can really advance our data procurement when it comes to point clouds. And point cloud creation tools are very much a development in the surveyor's toolkit. So when would you use reality capture over purely traditional survey methods? It's mainly on sites where you want to non-selectively get all the information around you. So with GPS and total station devices, you have to choose what you're capturing. You have to go out and selectively pick. But with reality capture methods, it's non-selective, it's getting everything in 360. This also carries the benefit that it's much faster than traditional methods. When you're going out with a GPS device or a total station, you're getting 1 shot or 2 per minute, but now you can get millions of points per second with these new methods. So data capture is a lot faster. The outputs, as you were seeing from that video just before, are much more visual and colorized often, so you can better understand those environments. This can be useful for a variety of stakeholder engagement pieces that we deal with in the AEC industry. And then there's also the benefits of once you've got this data, you can go back and measure from it at any time without having to worry about measurements that you missed. So it's very good for remote asset management. But there are disadvantages to this. The data is a lot bigger and the PC hardware requirements are very heavy. So for those of you that have done projects including hundreds of UAV photographs or laser scans, you begin to form a very close relationship with your IT person, and suddenly those M2 SSD slots, along with other jargon relating to graphics cards, RAM and CPU, become a little bit less alien. Hopefully your computer doesn't look like the one that was there. So there are 2 main point cloud methods. This is a very general look. There are a few different ways you can do this. But in general, there's photogrammetry, which is getting a series of overlapping images to reconstruct a scene. It's based off the idea of stereopsis, so binocular vision, having at least 2 pictures overlapping so that you can reconstruct the depth of the scene. And then there is laser scanning. So on the screen here, you can see a terrestrial laser scanner from a static tripod. It's got a pulse coming out onto a rotating mirror, and then the device is rotating to capture all the information 360 around it. There's also aerial and mobile mapping solutions, which all rely on sensor information and calculation of position to figure out all the measurements around it. A key difference between photogrammetry and laser scanning is that laser scanning is ground captured measurements. The points that are captured are fixed points, whereas photogrammetry is a reconstruction. So the points aren't necessarily fixed, they're calculated from those images. So for this reason, laser scanning is often seen as more accurate. This depends entirely on your project. And for those of you looking at large scale projects, the accuracies can become quite comparable. So it's more of a general rule that laser scanning is more accurate. So when it comes to point clouds, there's one key principle that you need to be taught straight away, which is structured versus unstructured. So what you can see here is a graphic I've made of 2 point clouds. On the left is some individual scan positions. With structured scans, each scan location, panoramic image and depth map is separate for each scan. It holds that information for each scan. But when you have structured data, so when you have unstructured data, you lose all of that individual scan position information. So what we've got here is a video of a structured point cloud. So this is a recap file, which is quite a good way to explain this difference. All the mirror balls that you can see here, or real views, show the positions of the scans when this scene was collected, and hovering over it, you're seeing those pictures. Then on the right, you can see all the individual scans. They have their own file for each point cloud, so each point cloud is separate there. Engineers quite like that because they can turn on and off individual point clouds in their Autodesk suites. But what you can see here is I've colored each scan individually by location, and now we have a very nice view of all the individual scans there. But this is a unified recap file. So what we have here is none of the pictures or scan location information. And when we look on the right, there's only one scan file in there. So that's that individual RCS file. So this means when you color it, you get one color. You have no information about the individual scan positions or any of that. So that's quite a general view from a recap point of view. There's different ways that you can see structured and unstructured, but from a general level, the idea is that you're retaining the structure of individual scans and the picture information. When it's structured and unstructured, you lose all that information. So many of the data delivered is often unstructured because it's a lot smaller in file size. As you can see on here is the sizes of those two files I just showed you. We've gone from 3.4 gigabytes with structured data to only 400 megabytes with unstructured. So again, it's retaining that individual position or location information, and it does decimate out when you unify the scans together and lose that information, which is what makes the file size a lot smaller. And the reason they're a lot bigger for structured scans is, as you can see on the left, for the recap files, it's got individual scan files, like for each scan along with all the pictures, whereas on the right, you've just got one overall point cloud together. So when it comes to scanning, there's a few different formats out there for point clouds, probably a lot more than I could show on the screen here. But these are just some of the main ones that you'll be interacting with. Point clouds are usually either in an ASCII text file format or in a binary file format. Binary is a bit more common. E57 files are probably the one that you will hear of the most when it comes to point clouds. These are kind of like the PDF of point clouds. They're quite fast and lightweight and can be read into lots of different programs. The most common one for that is actually ArchiCAD. When we go to recap files, they're a little bit different because it's both a format and a viewer. So you can open up the Autodesk Recap viewer that also passes around recap files. So that can get a little bit confusing. Some of the key things about all of these is that point clouds aren't always immediately visible. So with an E57, it has to be loaded into another program quite often, so that loading is called indexing. And to do that, you have to load it in and be able to view it after a certain amount of time has elapsed. So that's something to bear in mind, because for many of these, unlike the recap file, you can't just immediately see what's there. So then there's LAS and LAS files. So LAS is the key format for point clouds in GIS applications, and LAS is the compressed version of that. So this is what Esri and QGIS use quite a lot. One thing to note about LAS and LAS files here is the way that they're encoded can be slightly different for drone-based applications versus laser scanning applications. Drone-based LAS files often have the spatial frame, reference frame written into them, whereas the laser scanning data, it's often not encoded. So when you bring it into a GIS system for laser scanning data, you have to often project it to get it into the right format. And then some other common formats are PTX, PTS, and XYZ files, but there is a variety out there. LGS files and FLS, for example, are proprietary formats. LGS is the Leica TrueView one, and FLS are Faro scan files. So just be aware when you're dealing with point clouds, these are kind of the main formats that you're looking for. You don't automatically get meshes or PDFs from the data and DWG files even. So just be aware of that. So what are sources of error in point clouds? Last year, I got a load of phone calls from because a council had released an RFP for a 2mm of relative accuracy for a multi-story project. So for those of you deep into scanning, you'll know that 2mm across a multi-story building for a laser scanning project is practically impossible to achieve. This is because they'd been advised by someone who had looked at the specifications for a device, and that's the only factor that they had considered was the device accuracy. So I had very many calls that week asking if that was even possible. And whilst, yes, laser scans can reach that accuracy, there are so many other factors that can contribute, and achieving that over a multi-story building is very hard. Probably impossible. You can definitely achieve it in one scan, but then as soon as you start adding scans together, that's where errors will accumulate in different ways. So just to go over briefly some other sources of error, the environment is key. Are you in an environment with good geometry, or is there lots of moving objects such as trees and cars? Or is there lots of reflective materials causing noise? All of these factors can affect how your point cloud comes together. Weather conditions are also critical for outside capture specifically. Don't scan in the rain, folks. It's not just because it'll try and capture all the rain, but the water on the lens will affect the quality of your measurements. I did have someone after the Auckland floods call me and ask me to explain to them in detail how they could scan under an umbrella. And my advice would be don't try it. Weather is also a big issue for drones. On a drone, the internal barometer can be affected by the wind or the humidity conditions, and that can cause up to 30 millimeters of error in drone's recording of its flight direction and altitude, and that then affects the reconstruction of any data from it. So the positions of that airborne line or overall pictures will be off. Then we have field techniques. So there's going to be a whole section on this at the end of this presentation, specifically focused on terrestrial laser scanning. But the way that you overlap your scans, the way that you overlap your imagery, the ground control that you use, how it's spread out, the field notes that you take, and all those target naming errors that you can accidentally introduce into your point clouds are very fundamental sources of error when it comes to point clouds. And then finally, we have the registration process, how well everything has come together, largely based off those field techniques. But the key principle across all of this is the idea of accumulated error. Errors are not linear when it comes to point clouds. They build up throughout the project and are very hard to quantify without ground control checks. The larger the project, the more potential there is for this error accumulation. What I've got on the left here is a diagram where you've got tilted scans, so the up direction is off, but these errors can really happen in any direction, so you need to be very vigilant when doing your checks across your point clouds. Another key principle here is that once the point cloud is out there, it's very hard to retain any disclaimers on its quality. Some people put tags in their point clouds for lower accuracy areas, but this isn't a foolproof method because not all programs can read those tags. So you've got to be careful there with the quality of your point clouds when you're creating them. So what do we mean when we say quality assured point clouds? The first thing we mean is relative accuracy. Is the data dimensionally accurate for any measurements we want to take off it? And then the second thing we mean is absolute accuracy. So how accurate is your point cloud to the origin? So what I've got here is the moon, because you could have a very relatively accurate point cloud, but it's in the selenographic coordinate system for the moon. The third thing, which is not talked about enough, is fit for purpose. At the beginning of this presentation, I said it was about telling whether a point cloud is good or bad. And this may have alarmed some of you, because at the end of the day, point clouds aren't inherently good or bad. You have to look at them through the lens of the specific use case that you are capturing data for. So you will see in this presentation that quality certainly varies, but this principle of use case and fit for purpose is absolutely fundamental. So often this data is being used for BIM modeling. So cleaning and level of detail are key to this. Many companies don't clean their point clouds. In a situation like this image that we've got on the screen here, if the reflections were going inside the building and hitting other areas inside, and you had like a room reproduced inside a room, that can happen from the light hitting the windows on the inside at a certain angle, or mirrors reflecting whole rooms inside, that would definitely cause problems through modeling, and it will make it very hard for people trying to model from it. People and moving objects can also get in the way and make this modeling hard. And then fundamentally, we also have that level of detail. So what I mean by level of detail is the coverage of your point cloud data. If I was trying to model these pipes, for instance, I would have a very hard time because the coverage is so bad. You've only got one side of it. Trust me, I've tried just to test it out and see how it went. Many automated or semi-automated tools don't work very well with noisy or low coverage data. So this is definitely something to think about. You need good coverage for a lot of these modeling applications. So with these three quality assurance steps, measures in mind, this is what we're going to look at now. One thing I would say here before moving on is that accuracy is addictive. And as soon as the lowest accuracy is mentioned when you're talking with your clients, that becomes the sticking point, as was the case with that council RFP that came out here. So I urge you to work with your clients to find what is actually needed for that specific use case and be careful when talking about the devices and their capabilities. So here I'm going to outline 5 general checks that you can do, they're quite rough ones, for a point cloud that has come your way. So first off are visual checks. I remember looking at a point cloud for the first time and having no idea what I was looking at, thinking that it was absolutely awesome. Now, it's felt very wrong, but to avoid you looking at a point cloud and thinking it's great, I've introduced some errors into my own data to make it a bit more visible for you. The most common errors that you'll see visually are horizontal and vertical offsets. But before I show you the first one, I just want to point out that the person on the ground is a dummy on the left, is not real. So what you saw here is a point cloud that looked pretty great, but as soon as you zoom in, you can see that there's a horizontal offset, and this is about 20 mils. So when I'm doing training days, this is the most common one that people find hard to view. So it's just something to be aware of. What I've now got on the screen is a vertical offset. So this is just in the height where one point cloud is slightly elevated over the other. You can see here some yellow arrows depicting where those offsets were for the horizontal and verticals there. On the right, I've also got distortions and drift as something you should visually check for when you're just giving your point cloud a good visual inspection. So for photogrammetric outputs, I'd always focus around kind of the edges and then look for kind of distortions. That's quite common, for UAV or SLAM-based data, where you could have drift in the data where it's doubling up of features, or you've got, that blurring around the edges. Quite a lot of photogrammetric airborne stuff, they get 10 to 15% more coverage beyond the area of study to avoid that distortion that's quite common around the edges. Quite a good thing to do as well when it comes to looking primarily at terrestrial scans, especially when they're structured, is the classic cross-section. If you're able to color those scans individually, you can go in and see how well the colors are overlapping for those scans when you've got them individually colored. And then what quite a lot of people like to do is measure across them and get a bit more of an idea of how far off they actually are. And here, one thing I've just got to note is that when you're doing those checks and you're measuring across them, make sure that you're measuring properly horizontal, because quite often, depending on how the software is doing it, you might end up measuring across the height rather than across the cross section. So just having a nice and thin cross section will help with that. So checking that slice thickness is very important here. So if you're dealing with terrestrial laser scanning data, asking for structural scans is probably quite a good check that you can do. It makes it easier to do a lot of your quality assurance procedures, but that data will be very heavy. So if you can handle it, then I definitely recommend doing that, and you can always unify the data yourselves. So now what we've got here is a second general check that you can do. I love this one because it's so simple. This is a rough georeferencing check. So you can go to Google Earth, Google Maps is what I've done here, and just get your point cloud, which is coordinated, and go to Google Earth and just look at the north orientation of the building and just look along the edges and see that it's roughly aligned in the right position. You'd be surprised by some of the things you can find when you have a look that way. And that's also quite good if you have satellite or aerial imagery and you're looking at distortions in the data, especially for UAV. So the next one I've got here is rough height checks. This is my favorite. Height errors are the most common that you'll come across. So what I'm doing here is looking around this point cloud for some hard surfaces where I can pick some points. You want to have something that's hard. Obviously, this is rough because when you start picking those points, you don't know the exact heights of those points. So you're just looking for even surfaces just to look for general trends in your data. So what I've done here is just pick some points along the side of the point cloud, and you can see there's about 100 mils, 150 mils even, of difference in the heights across. So this is general. I could be picking on the wrong points, but the more that you do for this, the better it can be to track those trends and the values. But then what I've done is gone to the other side of the point cloud to do the same checks, just to see, because if you're getting a tilt in your point cloud on those hard surfaces, it will be spread throughout. So you can go and check around and see if that trend is continuing. And on this side, where I've got a larger hard surface, you can see it's a lot worse. I'm seeing over 500 mils of error here. So if you go into orthographic for an error that's that big, you'll be able to have a look from the side and get quite a good view of whether it's tilted. But yeah, it's a lot of error. So just doing those rough picks and getting those heights is quite helpful here. The fourth thing you can do as a rough check is overlaying existing information and seeing how it fits with the data. So this entirely depends on what data you've got available to you and the quality of that data. But as a general rule, just overlaying it and seeing what it looks like is very handy. And you can zoom into certain areas. Here I've got some total station data, so it's quite good for doing the checks, very good for doing the checks. And if you go in and do a cross-section of that data, you can colorize your point cloud as one color and just have a look at particularly the heights in those cross-sections and see if they're aligned. So here you can see it looks a bit out of whack. That's quite high up. So when you measure it, it's actually 40 mils off in height for that line. So one thing to be aware of there is that it could be you've got not enough points along when creating those total station line work. But more often than not, it's quite good to just use it as a general rule to see. If it continues across the point cloud, then you know there's something wrong. And what I've got on the screen here is quite a drastic example of where it can go wrong. Now, this is actually real data, not mine, but provided with permission. And you can see just generally being able to overlay and see what's going on. There can be quite obvious things that you can spot. So visual comparisons are good for spotting general issues, and you can go into a bit more detail with the cross sections, but that will depend on the existing information you are comparing to. So flowing through a lot of those, this brings us on to the final check that you can do generally for your point cloud quality. So what I've got here is some automated tools. So on the left is the Cyclone 3DR noise tool. Lots of different softwares have their own noise tools, and what's quite handy about them is that they're often looking for points that are far away within a certain 3D distance that you can set. So in this one, you can see that vertical error that I had in the second slide just before. And you could see that there was the point cloud slightly above it and below it, and it was obviously like some kind of point cloud that was misaligned underneath. What I've done here in that noise tool is just set it off to look for noise in the point cloud, and because there was so much offset and error in it, it highlighted the whole area underneath in blue and suggested that it be removed as noise. So it doesn't have to be the Cyclone 3DR tool that you're using, but you probably have a few different tools like that at your disposal that you could run over a point cloud just to see if there's any obvious errors like that. I have also heard that Topo.workflow is quite good for doing automatic checks on your point clouds. I haven't used it myself, but it's just something that I thought I'd point you guys towards to check out. So those are some general checks that you can do. We talked about some of the visual checks there, looking for your distortions, horizontal and vertical errors. We can do a general georeferencing check where you're looking just to see it's orientated north correctly, or that you're looking for distortions compared to satellite imagery. You can then do my favorite one, which is the height checks across hard surfaces, just look for trends in those Z values particularly, because that's the most common source of error. And then existing information overlay or automated tools. So that now brings you on to terrestrial laser scanning field techniques. And that's because field techniques are key. Quality assurance starts in the field. Beyond surveying, lots of people are picking up these tools and are able to get high accuracies. But as the projects get larger, those accumulated errors and their spatial distributions across the point clouds can be really hard to quantify and understand. So surveyors have a key advantage here in their ability to track these errors and their spatial distributions through those independent checks enabled by their total station devices. You can also do it with GPS, but we'll come on to that a bit more later. So when it comes to scanning and point clouds in general, these principles do also apply to UAV capture as well. we have three main ways that we can connect together one point cloud to another one. And the way that these are connected are called links or constraints. It kind of varies between different programs. The first is cloud to cloud. So you're comparing one point cloud to another and connecting them through that information. The second is vertex to vertex, where you're using a specific point in one point cloud and then comparing it to a specific point in another point cloud and using that to connect together your scans. And then you have a combined approach, which is using both. So I'm just going to go through each of these in a bit more and some field techniques that you can do that will enhance these methodologies. So for a cloud-to-cloud based workflow, you're becoming a bit like a professional puzzle master. You're giving an indication of where one point cloud sits compared to another, and then software does the rest to calculate the fit. So just then it was one red and one blue point cloud, and you're just rotating and fixing them into place to look at how they fit, and then also looking at the height as well. So from that, you get two scans and you start linking them together, and through this process, you can build up that picture. So this is just through cloud-to-cloud constraints. So when it comes to cloud-to-cloud constraints, the resolution that you're scanning at and the distance that you're having the scans apart is a really important consideration. If you're scanning at a low resolution, you're probably going to want to have your scans closer together to enhance that overlap. And then you've got to think about line of sight and the actual overlap between scans. If you've got good line of sight between different areas and good geometries, you can use that to pull things together better. I quite often like to look through the lens on my laser scanner and see if I can see some like edges of features and stuff when I'm a bit uncertain about what can be seen from one position. But then the final part of this, which is the most important for enhancing your cloud-to-cloud based registrations, is your scan patterns. And this is all about loop closure. So cloud-to-cloud algorithms can fall down in environments where there's lots of trees, moving objects, or repetitive environments. And often cutting and cleaning out trees or moving objects is required so that you're not bringing those two scans together based off those accumulation of points where the trees are, which have moved between scans and aren't very accurate. Different softwares have different levels of automation for this. But when it comes to repetitive environments, there's a lot you can do with those scan patterns and the loop closure that I was mentioning just before. And this is also quite a good example of where you can really improve the registration in general. So what I've got here is some stairwells, corridors, and tunnels. These are areas of key weakness when it comes to cloud-to-cloud registrations. So this is where you really want to focus on that loop closure. So if I was to just walk through that area in a line for a cloud-to-cloud registration, I've just got two kind of constraints, one between each point cloud. And this can quite often in those environments cause a horizontal offset. So this one's one I've introduced. It's got quite a lot of features, but in a tunnel environment, you will quite often get that offset in your cloud-to-cloud if you haven't got many of those features for it to hook onto, so it can't find common features to estimate the positions. This is where scanning in triangles can help you, because you're adding in an extra constraint for the calculation of how the scans fit together. And at the end of the day, all of this is statistics. It's using those fixed positions of the points to then calculate how they fit together. So you'll make your calculation more robust when you do it in this way. So here's a client that took my advice very literally, and it's absolutely beautiful. I'm very much in more of this picture. You don't need to go to this level of detail, but it is a good indication of kind of the direction that we're going in here. So the key bit of advice I was given when I started scanning was imagining that you're building a tin. You're trying to build a load of triangles. So if we go back to that corridor example, I'm not suggesting you're doing extra scans, but you vary those positions a little bit. And then that variation in your scan pattern can enable extra constraints, which will strengthen that scan pattern. If you could add an extra constraint by connecting the first scan to the last scan, if you did it in a line, but that's not really going to help with those horizontal offsets because you've not got the slight difference in what it's seeing there. These environments are also quite good for tactical targets, but we'll come on to that in a bit. So the same principle also applies with circular features. Instead of going around in a line for your scan positions, you can just vary the position slightly, and there's just one extra scan here, but you're getting extra constraints from doing it this way. So it's just making those calculations more robust. So what I have here is some hanging scans, and I've just highlighted with those yellow arrows. So for these ones, these will be unavoidable, and I want to emphasize here that when we say scanning in triangular patterns, we're not saying to go out of your way to do extra scans just to get triangles, but just to think about ways that you can vary your plan positions just to introduce some more loop closure to make those calculations more robust. So you can then just bear these hanging scans in mind when it comes to your visual QA checks. The idea with many of these tools is to make your field practice more efficient. So obviously, if we're going out and getting loads and loads of extra scans, we're not going to be getting those efficiency gains that we're after. So not always possible, but just think about loop closure. That brings us on to our second kind of constraint, which is vertex to vertex, so those point-to-point ones. So you can see here, these two scans in purple, pink, are connected just by those targets without any cloud-to-cloud information. So you can do this with identifiable features or black and white targets. What I've got here is the targets. So we've got black and whites. They can also be spherical, but you can also get them in like mini bipods, tall bipods. They come in all kinds of shapes and sizes, and having these push point cloud can be quite beneficial to doing checks of the distribution of those accumulated errors. So what I have here is identifiable features. Just going out and picking the edge of some paint can be a really good one. So when it comes to vertex, we have kind of three main types. The first two types are control points and checkpoints, and we're going to talk about those first. So control points are used to triangulate, reproject, and refine your data positions. They can be used to coordinate your data, and they're introduced into a registration process to varying degrees. And then checkpoints are also coordinated. They're not actually used to affect or modify the position of your scans, but they can be used for comparison. And then the last one is toe points, which can be not measurable in the real world, but are used to connect one scan to another. And sometimes you can have control, or you can have targets which are a mixture of both. But as a general starting point, if you're doing coordinated, so we're looking at those control and checkpoints first, you need a minimum of 3 targets for your georeferencing. And I always say you need more for redundancy, at least 5, but this will entirely depend on the size of your site. And you want to just make sure you have a good distribution of those. So fundamental to this is the control distribution. So if we go back to that earlier example where I showed you the quite drastic difference from one side of a point cloud to another with the 500 mils, with that example, there's quite a clear reason for how that actually happened. So what you can see here for that data set is that there is 3 control points that have been used on one side of the point cloud. And there's actually quite a large difference between the heights of 2 of those points, 200 millimeters. But if we go in and actually measure the height of that decking area, you can see that it's actually not 200 mils different. It's only 100. So error has been introduced by applying bad targets, basically. So when you apply those targets, the heights have to be maintained from one side of the point cloud to the other. Like here, because the Z's are all clustered on one of those coordinates that have been used, the heights haven't been maintained across to the other side. So you want to have that good distribution to stop that from happening. So if I was going to go out and do this site, I would have a nice spread of targets all around the site. So I'd maybe do one, some along the left-hand side and then around all the corners. If you're using a GPS, this is going to be difficult, especially with the amount of trees around, which is why these ones have been clustered on the left-hand side. But yeah, getting that good distribution is fundamental there because the Z has to be maintained at those positions when you're applying them. So when applying those 3 targets, the residuals actually came in really well for those targets, with 15 mils of reported error overall. And that just highlights, 15 mils is the highest residual there. And that just highlights the need to have some good robust checks in place when you're passing point clouds out or looking at your own final data sets. So with those rough height checks can be really helpful for an environment like this. So the field practice of having that good distribution will definitely help avoid those errors. So that's just the same thing. It's all clustered over to one side, but if you spread that out, you'll be able to get those Z values maintained across that point cloud. So this is really fundamental for SLAM-based and photogrammetric applications as well, because those are all one overall point cloud where you're applying those control marks to them. So a good QA tip here, if you're receiving point clouds rather than producing them, or even if you're doing internal QA procedures, is to ask for control distributions, residual diagrams, something to give you a bit more information about the checks that have been done on that data. So another key point I want to make here is that it's possible to apply your control to a locked or a unlocked point cloud. So what do I mean by that? Well, do you want to let your targets with your control fit to your point cloud and move your scans around? Or do you want to put them onto a fixed point cloud and get residuals for those errors without actually affecting the registration? So whether you decide to do it locked or unlocked, that affects the error propagation throughout the data set. I would generally, as a general QA rule, I would always say to start with the right-hand side. So you have your registration, and then you're applying your control or your independent checks to it and getting fixed residuals. So the reason I say to do that is because without affecting your registration, having those independent checks come in and say, this point is 15 mils out, or this point is 30 mils out, you get a really good understanding of the quality of your underlying registration. There are some scenarios, there are some scenarios where you might want to let the errors propagate out across the site. So when it comes to scanning projects or UAV ones that are going over quite a long area, you have to be quite aware of scale factor errors. So I'd still do that check first to see what the residuals to your locked data set come in as. But you might want to, in a scenario of like railways or roads, consider applying that to an unlocked point cloud. The reason for this is that many scanning systems particularly don't let you apply scale factor. And that's because of the belief that you've got the individual ground-based measurements that are measured on site, so they should be more inherently accurate than scaling it. So this is a problem when you're going beyond a kilometre and you can get 40 mils of millimeters of error in those residuals. So for roading errors, you might want to do your scans and let your scans fit to those targets and move around, so that if you've got really good total station control, you can fix those individual scans that way. And so what you're doing here is it's a bit of a decision as to whether or not you're letting your point cloud fit to each individual target in each scan, or you could break your point cloud apart and have an offset that way. But most people in this environment would let each individual scan fit to the targets, and then that way you're having a slight offset in each point cloud and you're propagating that 40 millimeters out across that 1 kilometer stretch. So you could use a combination approach there with your cloud to cloud and your vertex to vertex there. So yeah, many scanning systems don't allow the application of that scale factor, but that is highly dependent on which scanning system you're used, how that all works together. Another note I would make here on vertex to vertex constraints is, as a general rule, avoid applying GPS data to individual scans. So GPS data is generally less accurate than any of the scanning tools that you are using, and the XYZ values for that will be a lot worse. So if you allow that error to propagate out from a GPS device and set the positions of your scans, that will be affecting how your scans have come together, and you will probably see some errors with how they're fitting together. And any numeric checks when you apply control to a unlocked point cloud will propagate out those errors and make it look really good. So it'll be hard to get an idea of how those errors are spatially located. So when it comes to this, a very key thing to consider is how the Z level of your point cloud has been set. So there's many different ways you can set the up direction of your point cloud. When it comes to laser scanning, you could have a dual axis compensated device, which is kind of like the gold standard when it comes to your up direction. And then we also have IMU-based devices using their inertial measurement units. And then we also have leveled tripods. So one thing to bear in mind here is if you're using a leveled tripod, can your software actually recognize that the data has been leveled? Because if it's not embedded in the sensor, it might not actually be able to read that information. But those device Z levels might also be redundant if your control disregards, if the application of control disregards the Z values of those individual scanning devices. So what I mean by this is when you apply your control into your point cloud, different softwares have different ways of applying that control. You could have the control, whether it's your total station or GPS, average out with your scanning sensor information, or it could completely disregard the sensor information and purely use the control that you've put in. So for that data set before that we were looking at, the GPS values have been used and that disregarded the sensor information, which tipped the whole point cloud. So you've got to just be aware, that's the example from before, you just got to be aware how that control is being applied and how it's affecting that up direction. So carrying out all these independent checks and getting good distribution of them across your point cloud, and when you see errors, understanding where they've come from is really fundamental, and applying that to a locked point cloud is a good starting point for understanding your registration's quality. So just to go through some of those again, because I covered a lot there. Target distribution is fundamental for control. Your control can be applied to individual scans or the overall point clouds, so affecting how they come together. And different softwares use control differently. They might disregard or average those sensor readings and those control readings. Cool. So that brings us on to checkpoints, which is the other kind of coordinated. That's not as detailed as control points because it's not affecting the registration. It's more just a point of comparison. So for this one, you can go out, pick those identifiable features like the paint lines I mentioned before, and just check that distribution of error across the point cloud. So here I've got that data set from before where I just overlaid the information from the total station. And that was quite good. Just go through at different areas and see how it comes together across the point cloud. So it's not affecting your registration. It's just a good overlay. So if you're out there collecting points for your data, just going out and picking out some extra features and overlaying them is a good way to add extra checks to your data. Yeah. So that brings us on to our last type of the vertex to vertex constraint, which is tie points. They don't need to be measurable in the real world. They just need to be visible in the different pictures if you're using photogrammetry or laser scans, and can be used to say this point is exactly the same as this point in another scan. And that information can be used to tie those scans together without any coordinates. So I sometimes call it empty targets. But what's key about tie points is their use with tactical targets. So that's the third type of constraint I mentioned before, where you can have a combined approach of both your cloud to cloud and your vertex to vertex constraints. So when it comes to tactical targets, there are a few environments where this is particularly key. And those would be some of the ones I mentioned where there are some weaknesses in those cloud-to-cloud constraints. Another point here is that if you have UAV or SLAM-based devices, what you could do is have some targets set up across the point cloud that you measure in the field. Maybe you could use a disto or something like that, and just have an extra independent check for what the distance actually is between those two targets that you've put up, even if you're not coordinating them. And then you can check those measurements in your point cloud. But you'll do it from a known point to a known point, which helps with the accuracy of that check. So when it comes to doing the combined approach of tactical targets, I've got this diagram here from one of the Leica handouts. I'll find the link for that when these slides are sent around. But what you can see here in this diagram that I really love is they've done loop closure as much as possible. And then in areas where there's less loop closure, they've got more targets. So if you look at the center of that diagram in the corridor there, there's a load of targets around those scans where there's only one link between them, those ones that I was calling hanging scans before. So what they've really done is added in a load of extra links there to strengthen that registration. So here for that cloud to cloud one, I've got the inside of this school where outside it's all cloud to cloud, and then on the inside, as I've gone into the repetitive areas of the corridors and stairwells, I've just put up some targets. They're not coordinated, but they're good extra checks for strengthening those environments. And I didn't actually use all of these targets because the cloud to cloud here was quite good, but it's good to have them as a backup just to strengthen your registration in those areas. So repetitive environments, just putting up those targets will help strengthen those areas. So going back to that example from before along the corridor, simply putting up some extra targets, you'll get some extra constraints there for how these link together. And the same for here, just add in some extra information to strengthen all of the ways it's connected. This all comes back to the basics of surveying principles. You're working from the whole to the part, so you want to look at all the individual elements and start with a really good base of accuracy. So for here, we've got a data set that's been done with a dual axis compensated scanner, and then a load of really strong precision control marks being put in, and then the data's been infilled with some lower quality data on the inside. And that's just a good idea. You can have different areas of different accuracies and think about how that all comes together. So that was a lot of information. In summary, if you're still with me, laser scanning is just point and shoot. Sorry, I mean, not just point and shoot. So I'm just going to go over some of those principles again, just to summarize what we've looked at, because I understand if I've gone a bit far on some of that. But the key points that you really need to remember are, we've looked at some of the reality capture pros and cons. We've gone through different point clouds, types and capabilities, some of the main ones that you might come across. We've looked at structured versus unstructured scans, some general sources of error beyond just those device specifications, and then finally thinking about whether your data is fit for purpose. We then looked at some general QA steps that you can take. So your visual checks, your general georeferencing checks using satellite or aerial imagery, your general height checks, just picking points and looking for trends in those Z values, looking at that existing information that you already have for the site and overlaying it, and then looking at some of those more automated tools for these calculations. And then when it comes on to constraints, the key things here, it's all about the field techniques because quality assurance starts in the fields. There are two main types of constraints, which are cloud to cloud and your vertex to vertex. For cloud to cloud, thinking about your line of sight, those triangular patterns, if nothing else, the triangular patterns is what you should have got out of this presentation, and good overlap are key. There are three main ways you can use your vertex to vertex constraints. So that's your control, checkpoints, and tie points. And tactical targets can be used through tie points to enable that improved registration, those areas of cloud to cloud weakness. And when you're applying those control points, just be aware of your control distribution and how the software is using that control to set the Z level of the data. So how is that propagating out the errors in software? So some extra things you can ask for if you're receiving or QAing internal point clouds is for GCP positions and residuals, and perhaps a visual of your scan positions, just so you understand a little bit more about the distribution of those scans and how they're connected. At the end of the day, no point cloud is the same. So just be aware there's lots of different things that can go into this data, and those errors vary across the entire point cloud. So if you have any questions or feedback, please feel free to reach out to me at my email address of kirsty@globalsurvey.co.nz, and we'll now look at some here.